So, hi everyone. Today I'm going to talk about my ResilientDB application, which is ResCanvas. So before we get started with the application as well as how the background works along with my application, especially with the backend infrastructure, let's first talk about the basic concepts. So first of all, let's talk about blockchain. So what is a blockchain? A blockchain is basically a distributed digital ledger that securely records transactions across a network of computers, or otherwise known as nodes. And once the transaction is recorded, data in a block cannot be altered without consensus from the network. So basically what this means is that each block contains a set of transactions and a cryptographic hash of the previous block, and hence it forms a chain. And within this distributed network, every participant or node stores a copy of the ledger. So this means that there's no single point of control or failure. So as you can see, this entire concept of a blockchain is decentralized in itself. And because of this, nodes need to follow rules to agree on which transactions are valid through something known as consensus mechanisms. And this is pretty important because this whole concept of a blockchain guarantees immutability and transparency, since once the data is validated and added, it becomes tamper evident and can be independently verified by anyone in the network. So examples of these consensus mechanisms that I've mentioned in the last point here are proof of work, which is used in Bitcoin, or proof of stake, which is used in another platform called Ethereum, and also a practical Byzantine fault tolerance, which is used in a decentralized database called ResilientDB, which we'll cover later on. So next we'll talk about ResilientDB. Now I have mentioned this important database. So this is a very important part of this application because ResilientDB is a next generation blockchain platform which is designed for high performance, fault tolerance, and scalability. And it's a database that has implemented multiple designs to ensure that this is achievable. And the whole idea of ResilientDB was that it was developed to address the limitations of traditional blockchain systems, such as Bitcoin, that I mentioned in the previous slide. And it has designs for a high throughput, while also allowing for low latency as well as fast consensus. And it's also modular as well, so it's easily expandable. It's constantly being updated, and it's a active open source project because of this, which you can access via the link right here. So how ResilientDB works is basically a client submits a transaction, just like in Bitcoin, there can be transactions. It's the same thing in ResilientDB, either through REST, which is an endpoint that other applications can use, or GraphQL, which is a querying language that certain database uh, uh, applications can also use to query or interact with ResilientDB. And after the transaction is submitted, the leader node proposes a block in the chain, and replicas, which are the distributed nodes, validate the proposal. And after they validate the proposal, the individual nodes exchange votes and try to reach a consensus. So once consensus is reached, the block is committed, and then that's when the transaction becomes finalized. And the data is stored in the distributed ledger plus a database. So this database ensures that no single node can corrupt or stall the entire system. So there are several key components of ResilientDB. The first thing is the core. In other words, this core implements the PBFT-based consensus and the state replication. And there's also another component called Resilient Python Cache, where we'll revisit later on in this presentation, which is serving as the caching and fast transaction indexing for individual applications through its use of MongoDB. And then we also have the resilient GraphQL, which is the front end for submitting transactions through the GraphQL API. And then we also have wallets such as ResVault, which serves as like a cryptographic key manager for signing and verifying transactions. And then there's also other parts like the previously mentioned MongoDB, so on and so forth. So the important thing about ResilientDB is that traditional blockchains face three major bottlenecks. And the first bottleneck is that it has low throughput. So for example, Bitcoin can only process around 7 transactions per second. And they also suffer from high latency. So confirmation may take a while. For instance, it may take as long as several minutes. And it's also pretty inefficient because proof of work uses a lot of energy. It wastes resources. And basically, like ResilientDB solves these using practical Byzantine Fault Tolerant consensus instead of mining. Because as you might recall, like in Bitcoin mining, it has to use the proof of work consensus algorithm. And through proof of work, miners basically compete with each other using powerful specialized hardware like GPUs to solve complex cryptographic puzzles based on a hash function called SHA-256. In this work, the so-called work is a computational effort that is required to find a target hash, which is a very big hexadecimal number that must be less than or equal to a target hash set by a network. So in other words, the miners have to do this through guessing in a brute force way, and they have to guess trillions of combinations of a random number, or otherwise known as a nonce, to find the correct hash. And because of this, PBFT is much faster than proof of work because it's a collaborative voting process rather than a competitive brute force guessing game. So the PBFT algorithm allows for a defined leader and also a fixed known set of validators to allow transactions to be confirmed and finalized almost instantly through a set of voting rounds. So as you can see through this method, once a supermajority of nodes, which is more than 2/3 votes accept a block, the transaction is finalized and irreversible. And this method is pretty robust because a network of nodes can agree on a single result even if close to 1/3 of nodes fail or act maliciously, or otherwise known as Byzantine nodes. So this method is pretty efficient, yet it allows for consensus to be reached in a robust manner. And also allows for pipeline execution because it separates the ordering of client transactions done through PBFT from their execution. So this means that while the consensus protocol is running, transactions from a previous consensus decision can be executed in parallel using multiple worker threads without compromising the total order guarantee or the consensus process. And this is also pretty efficient because in terms of data replication and fault recovery, because we have optimized view changes, and through the robust view change protocol and checkpointing mechanisms, we can essentially efficiently elect a new honest primary node, which orchestrates the consensus process if the current one fails. So that way the system can recover quickly and maintain liveliness as well. So this brings us to my application. So what is ResCanvas? So ResCanvas is a real-time decentralized collaborative drawing application, which is built on ResilientDB. And it demonstrates live collaboration via a library called WebSocket and Redis. And this allows users to collaborate effectively and see each other's drawings in a decentralized way, because it performs decentralized transaction commits using GraphQL endpoints to ResilientDB directly. And this ensures that the user's drawings are securely stored because of this ResilientDB database, which is fault tolerant as well, because drawings can persist through across no failures and as such. And this is essentially one of, or the first drawing platform that uses a blockchain-based decentralized database as its backbone for storage. So why we need to have ResCanvas? So there are a lot of existing tools, as you might know. You might have used tools such as Figma, or Miro, or Google Jamboard. But there are several inherent issues with these existing tools that are available over the web. So first of all, the existing tools are centralized since it's hosted on company servers, and the collaboration model is also centralized as well since it's on a single backend server, and hence the data is controlled by the platform provider. And this also causes issues with regards to fault tolerance as well, because the single point of failure can compromise the server. And furthermore, in terms of transparency and auditability, it's limited since internal logs are inaccessible to users as well. So these are many of the issues with existing applications. However, ResCanvas is decentralized as transactions are recorded on the ResilientDB blockchain. And also they appear synchronized through Redis, MongoDB, and blockchain. So that way you have a layered, tiered implementation where users can collaborate effectively without worrying about the consensus process that occurs on the backend. And this brings a whole host of benefits because the data is thus user controlled and cryptographically signed. And it's through PBFT. It's also very fault tolerant as well. And because of this blockchain-based backbone that ResCanvas uses, it's fully auditable, and other operations are logged on the chain and cannot be altered. So now we know the benefits of ResCanvas. So the main features that this application implements is as following. So basically we have multiple users that can draw concurrently and view the editing history. So this application functions basically like a Google Docs or Google Drive. And also like Figma, you can see the editing history for each user, and also it has the timestamp. And this is also occurring at a per user per room basis with custom room and user access controls. So that means that users can place restrictions on certain people. Maybe some can only view the room, or others can have editing permissions similar to existing web-based apps. And this drawing data and edit history is synchronized effectively and consistently through all users within the Canvas drawing room. So that allows for fast, efficient data loading from the backend, because this application implements a cache that is called Redis. And this Redis cache allows for data to be called back quickly. And we also show this in the following slides when we talk about the end-to-end data flow. And the next feature that this application has is basically a JWT-based authentication for the API, and also socket IO access. And through the socket IO access, you can perform real-time collaboration for low latency stroke broadcasting, notifications, and user activity communication. So this allows for users to see like who joined the canvas and who perform a drawing, or also like if the user sends a room access invite to another user, that user also receive that notification through the socket.io library as well. And this can all be done in a secure manner. So there's no sharing of data to any third parties or advertisers or governments, so on and so forth, because of this decentralized nature of ResCanvas. So speaking of the collaborative features, here is a brief rundown of the specific features that my application implements. So the first thing is the thing that I previously mentioned with regard to room-based collaboration. Users can create or join existing drawing rooms or new rooms, and each is backed by its own Redis and MongoDB workspace. So this allows for isolation of session data between users, as well as scalable multi-room collaboration. So it's the best of both worlds. You can either have like a secure private room, or you can have a scalable private room or even public room where multiple users can collaborate on the same canvas. And through account management, we have GWT secure login registration system, which is implemented in Flask. And this allows for credentials to be hashed. So that way everything is secure, and the authentication is integrated within the Redis for caching for quick validation. So if the user logs in very frequently, that will be cached as well in the Redis. And the most important thing in terms of the user experience is that ResCanvas offers a dashboard and also a sharing functionality, similar to apps that you might already been familiar with. So the central dashboard lists all the rooms and the shared public, private, and secure type rooms. And you can also generate share room links to control access, and also notifications to other users if necessary. And speaking of undo redo, which is one of the core operations of ResCanvas, it can be done just like in any other app, but here they are committed to ResilientDB just like strokes, which allows for replayability. And on restart or Redis flash, the app rebuilds the state directly from ResilientDB. And real-time collaboration allows through the socket.io allows for a quick broadcast of any event. So for example, if a user draws a stroke or places a stamp on the canvas, that will show up on the other user's canvas due to the socket.io communication channel, which basically pings the other user who has access to the same canvas and allow that user to see the stroke happen in real time. So the key components, just quick rundown through them is I implemented the front end through the React library, and this handles all the input, display, and the UI state and the socket.io that I previously mentioned. Also leverages the local storage and the front end API wrappers to attach the necessary authentication-based information such as JWT tokens, and it contacts the backend to perform all protected requests. So speaking of the backend, backend is implemented through Flask as well as Flask socket.io. And this backend serves as the authoritative security boundary, which validates all JWT tokens server-side using middleware. So what a middleware does is it uploads the validation and authentication tasks to the backend, and the middleware serves as basically a middle part between the front end to the backend. So it's like a manager that ensures that all requests are protected, but we don't want to perform the validation client side or on the front end, because the client can change the code and try to find a way to access the forbidden requests, which is like accessing secure rooms or trying to access the drawing data without being a valid registered user. So we don't want that to happen. So we have a middleware in this backend, which enforces the room membership, the permissions, and verifies client-side signatures for secure rooms. And also the backend besides the middleware, it also encrypts, decrypts strokes for those private secure rooms and commits transactions to ResilientDB via the GraphQL. And we also have ResilientDB, which I previously mentioned, which is used extensively, which in ResCanvas serves as a persistent, decentralized, immutable lock, a transaction lock, where all the strokes are stored. And each stroke is, in essence, a transaction, like a transaction in a Bitcoin. So that way the full history is auditable and censorship resistant. Nobody can change the chain of transactions. However, we also have a MongoDB, which serves as a warm persistent cache, and it's a queryable replica of strokes. So that way the backend can serve reads without contacting ResilientDB directly for every request. So there's a sync bridge, which I mentioned as a resilient Python cache, which mirrors ResilientDB into MongoDB, which allows us to do reads much more efficiently. So besides that, we also have a Redis cache, which I mentioned previously as well. This Redis cache is a short-lived in-memory stored key by room type of cache. So this allows for even faster rewrites and undo redo operations, especially if a user has a ton of strokes on the canvas. This Redis cache helps with the latency because it is intentionally ephemeral. So ephemeral means that it's short-lived. That the data is short-lived on the in-memory data store because it's stored on the node's random access memory, which requires, as you know, requires continuous power to retain information. And in other words, it is a volatile memory as well. And this cache is basically like a warm cache because it's like a much warmer cache than MongoDB because ResilientDB is a long-term durable store, and Redis allows for data to be loaded back much more efficiently. So basically what a warm cache is that it's ready to handle requests with a better speed than a cold cache. And as Redis populates more and more data, it can become something what is known as a hot cache because it's fully operational and the cache is heavily used and it has hit the highest hit rate, maximum efficiency, and the fastest performance. So you can think of it like an engine running at an optimal temperature once it warms up. So now that we know the key features, the key motivation behind ResCanvas, let's take a look at the architecture. So basically what we can see in this diagram here is two users who are using ResCanvas. So on the top here is this user 1 and user 2, and they draw strokes. And what happens is that the strokes get pended in a pending drawings queue. And from the queue, the stroke payload is submitted one by one to the backend. The backend, when I was developing ResCanvas, is running on the dev server of ExpoLab. And this dev server here has the cache, the Redis cache that I mentioned, and also the undo redo stacks cached in here as well. So what this allows is for strokes to be submitted quite efficiently because as you can see, after storing the stroke in the Redis cache, the stroke is also written into MongoDB and submitted to ResilientDB via its GraphQL endpoint simultaneously. So the reason that we do this is because we want to read back the strokes quickly. And thus the resilient Python cache handles this by interacting with this ResilientDB backend. And the resilient Python cache allows MongoDB to be repopulated from ResilientDB and thus stay in sync. And through MongoDB, we we ensure that Redis cache is also synced up as well for the best UX. So now that we know the key architectural overview, let's take a look at the front end to back end data flow when a user draws a stroke. So first of all, after a user has done that, it's sent as a JSON data structure, which is pretty common. And this JSON is basically sent by a post operation via the method submit new line rule. And this method basically contacts the backend. And once the backend gets contacted and receives this new stroke JSON payload, it validates the stroke and then unwraps it if it's valid. So the reason that we validate it is we want to make sure the stroke contains all the necessary data fields. For instance, the most basic stroke that ResCanvas has contains fields such as the color, the stroke path, which is the XY coordinates, also the brush type, like is it a fuzzy brush, is it a normal brush, or is it a blurry brush, so on and so on. And also we have other necessary information, like for instance, who drew the stroke, what is the username, the timestamp, when it was drawn, so on and so forth. And because of that, we need to validate it, just to make sure we have all the data. And then we can unwrap the payload and then build the transaction payload with this stroke data plus other necessary information based on the user's login, the user's account information. So this login account information contains other relevant information such as the user's public private key, and we need to add this as part of the transaction payload because we're treating it as like a wallet type transaction. And after we build this transaction payload, we can commit it via GraphQL, which sends this payload to the ResilientDB server. So after we send it over, they perform the consensus, and then after that's done, we get the commit success acknowledgement from ResilientDB. And after we get that acknowledgement, we can broadcast the new stroke to notify peers that the stroke is valid, and they can keep the stroke on their canvas. And also we push this stroke to the Redis cache as well as MongoDB. So here, as you can see, that we committed and we also push the stroke. And then once we acknowledge, we get the success acknowledgement back, we can broadcast this to notify the peers of this new stroke, which is valid, and they can keep it on their canvas. So this is what happens here, and we return it back. And then that user's end will see that new stroke appear on their canvas. So now that we know how the front end contacts the backend, now let's see how the backend contacts ResilientDB on a lower level. So the stroke payload is received from the ResCanvas backend, and it goes into the commit endpoint of ResilientDB. And for my application, I chose GraphQL because it allows for more efficient querying later on with MongoDB and so on. And this new transaction here goes to the consensus flow, the PBFT consensus, where the leader receives the transaction. This leader is also known as a primary node, and then the followers validate and vote on this transaction, this new stroke. And then once they aggregate the votes, it reaches the PBFT threshold, 2/3. It can commit this transaction. And how does it commit this transaction or the stroke? It forms a new block, or block n, the nth block of the chain. And afterwards, it does two things. It sends through WebSocket update blocks notification to notify the library resilient Python cache sync bridge as a WebSocket event. And the whole purpose of this notification is to allow the sync bridge to get notified and be aware of ResilientDB, because once there's new data in ResilientDB, we need to let Resilient Python cache know about it so that it will know to sync up with ResilientDB again and fetch the new blocks that have been committed in ResilientDB so that MongoDB can stay and sync or with catch up to ResilientDB's newly committed transactions. And after that happens, we also have acknowledgement that we send back to the client, which I previously mentioned allows the client to know that its stroke has been committed successfully, and also allow the front-end users to be assured that their stroke can stay persistent because it has been consistently committed and everything is working as it should. So moving on from that part, let's take a look at how ResilientDB contacts MongoDB through the resilient Python cache sync bridge that I've been mentioning, and then how it returns to the front end. So starting from the right here, we have the sync bridge. So that update blocks notification is something that resilient Python cache knows that it needs to listen to, because it has a listener set up that listens for this very specific notification. And once it receives that notification from ResilientDB, it pulls in the blocks, the newly committed blocks, and it fetches it through a REST endpoint. So it doesn't use a GraphQL endpoint, instead uses a REST endpoint, but that's okay because we're getting back a block JSON, and we're doing that for all committed blocks. So we're not searching for specific blocks. Instead, we're doing it for all committed blocks that have been in ResilientDB and committed successfully. And then after getting the blocks back, we parse the transaction JSON. And then through the JSON, we perform an insert operation, which is commonly done in MongoDB to write the blocks into that collection. And speaking of collections, MongoDB has two levels of collections. The first one is a block collection, which is containing the block by block organization of data from ResilientDB. So it basically serves as a mirror of ResilientDB. But within the blocks, we have a lot of data. So we just want to get the strokes out of the blocks. So what we do is we flatten the transaction, and then we get the strokes from the flattened transaction blocks. So from those flattened blocks, we get the transaction. And from the transaction, we get the strokes, which is stored in the strokes collection. And from the strokes collection, the backend, through its read path, can get the drawing data for its particular canvas room through its getStrokes function. And it takes in a room ID, which is the specific canvas room. And then that's how we can get data from MongoDB or a Redis cache, depending on whether the cache has the data or not. And then it returns the drawings back to the front end. That way the end user sees the stroke data. So going into a bit more detail about other functionality of my application, the first thing is a user authentication. So what happens here is that a user, for instance, if you're a new user, you register for a new account, and then the user's password is hashed via a bcrypt library so that nobody can steal your password and see what it is, and create a new user entry in MongoDB. And then this user is saved and generated, and with user is saved and the JWT tokens are generated and returned back. And that allows the user to access the protected parts of ResCanvas, such as like the private drawing rooms and its data, user settings, so on and so forth. And this data is stored in the browser's local storage. So the key parts of the local storage that I use in terms of the type of data, the first one is an access token, which allows the user obviously to log in and access all the drawing rooms and the data, so on and so forth. Also, there's a refresh token, and this refresh token allows the user to stay logged in even after a while, but there's a set time and the default is 7 days. And auth user just shows the username, so that can be handy for like sharing the username with other users and also see that you have been logged in and among other usages. So in terms of the stroke read path, what the front end does is that it first performs a GET request to this endpoint here to fetch new stroke data. And this endpoint basically contacts the backend, and the backend, as you know, it tries the Redis cache first, and then if there's a cache hit, then you can return the data back quickly. If it misses, you fall back to MongoDB, and then the MongoDB, if we fall back to it, we will get the stroke data from the strokes collection to populate the Redis cache, and then we return the data from there. And then for the write path, the user A draws a stroke on the canvas, and is indexed by the room and the user ID. And this is sent as a post request to this endpoint right here as a JSON payload. And then this JSON payload is cached to Redis, is sent to ResilientDB, as well as MongoDB as well. But here we show ResilientDB only because here we have a GraphQL mutation that I want to illustrate more in a different angle. Because after we submit the stroke, user B will see that user A has drawn the stroke data, and the socket out broadcast emits the stroke data to user B's front, and then it will receive that stroke broadcast and render on its own canvas. Once it is a 200 success, which is returned back to user A. And then at the same time, we have this background sync process that I've shown before. And this ResilientDB, through its WebSocket, commits a new block or transaction, and it allows a sync bridge to know about it. The sync bridge parses the stroke data from the block and sends the parse data to the MongoDB. And it also sends a 200 success acknowledgement of insert success into MongoDB. And this cycle, from this flowchart, you can see it runs a cycle. So it goes in a cycle. This library right here runs consistently. It runs constantly. It's never stopped or restarted unless absolutely needed, because it's listening for new block transactions. So there's several working parts of ResCanvas that integrate together. So with that in mind, my core contributions to ResCanvas comes in 4 major components. So the first one is the end-to-end system architecture, which I integrated React, Flask, GraphQL, Redis, MongoDB, and ResilientDB together, and its associated integration. And I also implemented the JWT authentication for login, registration, session handling, and also the GraphQL commits and recovery flows, so that Redis and ResilientDB are consistent with each other. As for the block backend development, I wrote the Flask raw handlers for submitting new strokes, the undo redo operations, as well as like the history recall and room-based collaboration. So I also designed the transaction schema, which is like the stroke JSON with the color, path data, brush type, and also like the user and room related metadata, as well as the timestamps for each. So like the user metadata will contain like the username, like the user's rooms that he or she has in his account, and so on. And also leverage our ExpoLab's resilient Python cache library to fetch the committed box and sync the Mongo collections with the Redis. And for the front end, I built the modular canvas interface, which supports stroke drawing, cut and paste, undo redo, the various tools like drawing shapes, like circles, rectangles, hexagons, also like a dynamic selection of different drawing tools. Like there can be different brushes, with different colors and thickness, styles, and so on, as well as real-time synchronization. And there's also a dashboard which allows users to select different rooms and allowing users to like join, create, or share collaborative rooms, as I'll show later on in the demo. And in terms of the blockchain and research layer of my application, I adopted ResilientDB's consensus algorithm for real-time application workloads. So this application is essentially one of the first one to leverage ResilientDB consensus based protocol database for real-time workloads, like for drawing. So it's going beyond just Bitcoin, and we can just even perform drawings on the canvas. And I also show that GraphQL-based transaction commits, fault recovery, and full stroke auditability is performable because you can perform history recall on ResCanvas. And it's also low latency because of Redis. And with that in mind, I can start the demo of my application. But before that, first of all, you can see that my project is freely available on the Resilient app, and the repository and the README is available online with the relevant setup steps and brief introduction. And in terms of the demo, what the first thing that the user will see is a sign-in page. So once the user creates an account or registers, they will go through the typical sign-in flow. So once the user signs in, they will see a dashboard here. What this dashboard shows is the rooms that I previously mentioned, and also like secure rooms, which require a wallet signing, as well as like archive rooms. You can delete them, you can archive them, and then delete them. And you can also search for public rooms right here. Like for instance, there's some rooms called public rooms or public 3232 if you want to join. And there's also several rooms that you can go back to. For instance, if you created some rooms and you already performed some drawings, you can resume drawing in those rooms. So for instance, this room has some colorful stamps, some custom strokes already in there. And you can see that drawing history shows each of the user's drawings in a sorted manner according to when it has been drawn. And the highlighting of the drawings show these are the relevant ones drawn at this time by test user 2. So here the user can put some stamps. They can do all the operations that they are familiar with. They can change styles. They can also change some effects of the canvas, just like any other drawing program like Figma. They can also select different colors, and they can also draw shapes, as I have mentioned before. So in the shapes here, they can do these operations, and also they can cut and paste as well. And those cut and paste works with all the strokes, including shapes, so on and so forth, with the informational tooltip for saving the cuts, segments, and so on, because each of them is like a transaction in itself, which takes some time. And then pasting also works similarly as well. The user will see that some transactions occur quickly because I implement some preloading algorithms and mechanisms so that users can see, for instance, this stroke right here, even as it is being submitted to the backend. So you might have seen like once I draw the stroke right here, it loads a while before the loading drawings appear. So this is the time that it takes for the stroke to be actually submitted to the backend and waiting for the backend, waiting for ResilientDB to respond back with a success acknowledgement. But the user can see that his stroke already appeared immediately. So this is pretty instantaneous in terms of the UX. It's pretty smooth, and I can pan around and draw somewhere else if I so choose. So this canvas allows for big drawings, not just small ones. And previously I mentioned about the secure room. Right now, I don't have a wallet installed because we have ResVault, which is available as a Chrome extension. You might notice I'm running on Firefox. So what happens here is that I cannot draw because this is a secure room. Hence, the canvas is locked. And if I try connecting a wallet, because I don't have that extension, it will just load, keep loading, keep connecting, and then eventually it will time out and then give you some troubleshooting steps right here. And this is just some of the functionality that I have for ResCanvas. There's also other functionality like notifications. I was doing some testing for the past couple of weeks, and I was transferring ownership of a specific room to other users, and hence I can get notifications like when I'm the owner of a specific room, when other users give me ownership to the room, or when I transfer ownership to another user, this will also appear here as well. Or if I was downgraded in a specific room, for instance, if I was previously an editor in this room and it has been changed to viewer by another user, I'll also receive a notification as well. And if this notification is too much for you, you can change your preferences here as well. And also, besides canvas room of different types, you can also archive them. So archiving means that you can hide the room and from a normal list, like for instance, if your list is too long, you can archive some rooms, and from the archive room, you can delete them so that they no longer appear. And this is pretty secure because, for instance, if I was locked out and I tried to look at some of the rooms, like for instance, if I was locked out, this room will not appear. So I got immediately taken back to the login page. So going back to the dashboard, if I try to do that, I'll just get redirected back to the login page. And besides that, I also implemented metrics to benchmark like the different layers of ResilientDB, like ResilientDB, GraphQL, Mongo, and Redis. And also there's a blog built into my application as well. There's also a help page right here, which also has a link back to the blog. So this is the log out state. You can register or log in. Yeah, and that's pretty much the whole overview of my ResCanvas application. And if you are interested in learning more about my application or want to get started in hosting your own ResCanvas application or want to contribute to the project, you can check out the repository right here. And the repository is also available in my slides as well. Yeah, and thanks for watching.